So this talk is about SpacetimeDB. It's entitled Database-Oriented Design, or Why We Built Our MMORPG Inside a Database. So that's a very interesting question, and that's what we're here to answer today. But a little bit of background about us and who we are before we get started there. So we are a company called Clockwork Labs. We're a 40-person game studio, and we're developing an MMORPG called Bitcraft Online. So Bitcraft Online is a fully persistent world, single world MMO where all the players are in the same world, and they can edit the terrain and build buildings and cut down trees and build whole societies. So that's what we set out to do. And I just want to go through a couple of pictures of the game to give you a sense of what it's about. So here, for example, this is a player-built settlement, and you can see actually that's an emperor there with a crown. This is, you can build anywhere you want in the whole world. So these people built like a seaside area, and you can see a road going deep into the background there. You can edit the terrain, as I mentioned. So here we have somebody who built a pit. It's a very nice pit, if I do say so myself. It's an MMO, so you get a lot of players. You can get a lot of players in the same place, and they're all working together. We have all kinds of outfits and ways that you can skill up. So it's a sort of a long-term progression game, kind of like a mix between, I suppose, RuneScape and Minecraft, if you want to think of it that way. It's a survival crafting game, so you can die. Don't do that. This person is having a rough time. That is very sad. We have a whole bunch of biomes. You can see here are 6 of them. They're beautiful. The art team has done an amazing job. Super proud of them. It's a really, really cool space to build a city. The map is enormous. So here is a map of one of the alpha worlds. And just for context, I think this was about a month of somebody exploring the world. So it takes a lot to get through the entire world. In future worlds, it's going to be even bigger. We have a really, really awesome Discord community. Definitely join the Discord if you can. This is an example of somebody who actually took our map and made it like a beautiful art piece from it. And the world is called Starfell, which you can see there. So shout out to Porcelain Towers on Discord for that one. There's some really beautiful environments. You can kind of get lost in the world. As I mentioned, we have all the different biomes. So this is what we set out to build. And I guess the first question is, why on earth would we do it inside a database? So at first, it seems absolutely unhinged, and with good reason. Why would we do it? Would it be too slow? What does it even really mean to run inside a database? Can you do it? Is an interesting question. I actually believe it might be the only sane way to do it, and I hope that by the end of this talk, I can convince you that maybe it's not unhinged at all, but it's actually eminently reasonable. So that's what we're setting out to do here, especially if you want to build a fully persistent, fully editable world like Bitcraft. So this talk could have been about a lot of things, the performance of SpacetimeDB, the innards of SpacetimeDB. We're going to go through a little bit of that, but let me just take you through the table of contents. So we're going to go over the technical requirements of what you would need to build a game like Bitcraft. What does it require? We're going to go over how you might do this in the traditional architecture. So there's a lot of different architectures you could do. There's sort of a standard-ish one that you might apply to MMORPGs, and we'll go over that. We're going to go over the challenges that you're going to run into with that architecture and how teams try to solve them, but the difficulties with that. We're going to go over our approach, what we did, how it's different. We're going to go over how that eliminates a lot of the challenges that you would normally get in an MMORPG. We're going to touch on how it works internally, just to kind of answer some questions there. And then we're going to go into some really cool bonus capabilities that SpacetimeDB gives you that you wouldn't even have thought about unless you had built it in a database. And finally, we're going to go over a couple of future ideas and some parting thoughts on data-oriented design in ECS. I'm going to try to keep it short because I think people are going to have questions, and I want to leave some time for that as well. But yeah, that's the talk, so let's get into it. So the technical requirements. So this is a big game, obviously MMORPG. The first thing we're going to need is a single physical world. So every player is in the same physical world. It's not as if we could phase it. So you can't have one region of the world where many players are all in the same place, but they can't see each other. The reason is because you can edit the terrain, and you can build buildings, so everybody needs to see those buildings. We need to have, if we're going to be a successful company, possibly 100,000 concurrent players. They don't have to all be in the same physical place, but we need to be able to build that somehow. You need to have probably about 1,000 players in the same region. For it to feel like an MMORPG, we want people to be building big cities. They want to see people walking around, be able to trade with them. We need them in the same place. It's an MMO, so we need server authoritative logic, and we're going to have very complex permissions potentially. So we want people to be friends with other people. We want you to only allow your friend to be able to open this chest if you're above a certain level of health or something like that. All of the character state and all of the world state has to be editable. So that means, normally in an MMO, you don't really change, let's say, the city that you're in, but in this case, you obviously do. Not only that, but it has to be durable, also known as persisted. So we need to, if our servers turn off, you don't want to lose the cities and the buildings you just created. Some transactions are required to be transactional. So if I'm doing a trade, I don't want gold dupe bugs where I copy the items and then before I actually delete the items from the source, I throw an error or something and now we have a duplicated item. The character and world interaction has to be real time. So obviously if I'm fighting a monster, my health needs to update in real time, my stamina needs to update in real time. Potentially also, I need to be attacking a tree and doing damage to that tree, so that all has to happen in real time as well. We need to have thousands of mobs in the game, right? So there's thousands of players, and they need to be potentially being attacked by the jackals that you saw earlier, taking that player down, so that's an important component. We need proximity chat. We also need this to be tractable to build for a team of about 10 developers, because that's what we had to build it. So that's the challenge. It's a big one, but let's get started. So we're going to take a moment to go through the traditional architecture. I'm going to simplify. Let's not care about scale. Let's just try to get something working that actually implements what we need to do at a smaller scale. What do we need for this? Well, we're going to need a game server. That makes sense. We're going to need a game client as well. We're going to need probably a web server so people can log into our web portal and maybe see their items and things. We need a database for the persistence. We're going to need some way to deploy it, both locally for development and then also when we want to deploy it live. And then, maybe we have like data analytics or a chat server or something like that, but we'll consider that bonus material. Let's see how hard the problem is when we scale it down to just the bare minimum. So here's approximately the simplest architecture you could imagine for this. Here we have a bunch of clients, and they're connecting to a game server. And that game server is connecting to a database, and the web server is also connecting to that database. We're going to forget about the analytics and all that for right now. Let's take a look at the game server state in this case. So we have some ephemeral state that we need to be updating in real time. And we have some persistent state, and that persistent state needs to be durable and stored on disk. And it may or may not need to be updated in sort of real time. We'll see how we can deal with that. But it does need to be sent down to the clients and synchronized with the client state. So this is approximately what that would look like in the traditional architecture. You have your ephemeral state up at the top, and you have your persistent state, which is also stored in the database, but you need it in your game server so that you can send it down to clients. And anytime it changes, you need to be able to send that down to clients. Maybe we load that into the game server, I don't know, when the database starts up. Well, we're going to run into a problem immediately, which is that we better hope nobody else is writing to the database at the same time, either from another process like the web server or from another thread, maybe even in the game server, because we have now two mutable states on two different machines. So if the web server writes an item into the database, the game server doesn't know about that, and it doesn't send it to clients, and now the game server might be operating and mutating the item state and you're going to have to reconcile this state desync at some point. It turns out this is not a trivial problem. This is perhaps one of the hardest problems in computer science. It's distributed consensus. We have two machines, and they need to be in agreement as to what is in the item state there. It's also related to one of the two hard problems of computer science, which is cache invalidation. So that's a fun one. You could think of the game server as sort of a write-through cache. So that would mean that you have every write go through the game server, and you forward it on to the database from there. So, SpaghettiOs. Step one is solve the hardest problem in computer science. Cool. We're off to a fantastic start here. As I mentioned, one solution you could do is, okay, well, fine. What we're going to do is we're going to treat the game server state as a write-through cache, and also we're going to make sure everybody reads from the game server state. So nobody's going to go to the database. We're going to lock the database away behind walls and walls and walls, and everybody must use the API of the game server. And so here you can see the web server is talking to the game server, which is going to talk to the game server state, and the game server has to make sure very carefully that any state that it writes is sent to the database, and that we never read from the database without going through that state. Okay. So for example, if we have items here that this web server wants to change, the web server is going to make a request. It's going to update the items in the game server state, and then it's going to push that through to the database. Yes, so that's fun. I'll note one thing here, which is that we could have something like SQLite, where the persistent state is actually going to be inside of SQLite, and we embed the database inside of the game server, so that we maybe don't have to treat the game server like a cache, and we can keep a lot of that state inside the database, and anytime we want to access it, we just edit it right inside the database. But already, we're seeing that, it might be interesting if we combined the state of the game server and the database in this case. This has some other problems, which we'll explore in the future using SQLite, in that it fixes some of your problems, but not all of your problems. But we're getting an idea that there's maybe something here. Okay, so that's the database in the game server. Let's go through the game server loop. It's pretty simple. We're going to process player input. We're going to simulate our AI. We're going to simulate the world. And then we're going to publish changes to clients. Not too bad. That's what we do in any game that has multiplayer. Hold on a second, though. Before we do that, before we start writing our game, we got to make sure that we have our data layout optimized for cache efficiency, right? We don't want to build this in a way and then not be able to actually handle the number of players that we need to handle, which, by the way, is 1,000. As we remember from before, they have to be in the same place. We need to decide how we're going to periodically or selectively store the data to the database. So I mentioned the write-through cache method. That might not be sufficient because you might need to edit the data more frequently than you can write it to the database. So in that case, what you want to do is keep the state all in the game server and periodically write it to the database. We need to implement serialization and deserialization. We need then a messaging protocol. We're going to need a transport layer. By the way, we want to be able to use maybe system types or game engine types, so we need that type information as well. We need to also implement an area of interest broadcaster, something that's going to tell the clients about the data as it changes in real time, and that needs to be something related to where they are physically in the world, although they also will need to get global data as well. We probably also want to think about multi-threading, because if we do this wrong, we can't kind of go back in time and address that unless we've been a little bit careful about it at the beginning. So we haven't really started yet. We need to do all this first. Let's do all that first. Also, by the way, once we're done prototyping the game server, we're going to have to figure out authentication. So, okay, that's fine for prototyping, but we're going to need to figure that out. We need to actually implement multi-threading. We'll probably need to do some analytics, and maybe we'll have some admin APIs, and we may have some admin clients, and maybe an AI client or something like that. So that's the game server. Let's go to the game client. We still can't really start building our game yet. We have to also do the serialization, deserialization on the client. Hopefully we can use the same code there. We have to hook up the transport layer on the client. We need to do the messaging protocol. We might need to do something like client-side prediction, something like that. We'll see. We definitely can't store the full state of the world on the client, so we can't do any like deterministic simulation because it's an MMO, so it's a huge amount of state. And then we got to deploy it, by the way. So I guess we will run it in development with Docker because we got to start the database and we got to start the game server and we got to start all of our services. We probably have to set up our AWS account and all the permissions. And then to deploy it to the cloud, well, we can't just use Docker because we need to have a cluster of these things. So I guess we'll use Kubernetes and we can set up a proxy and we'll set up some networking. And by the way, we haven't even begun talking about how we're going to scale this thing. This is just the bare minimum to get started building an MMO. Once we scale it, okay, so what we're going to need to do is we're going to need to have a bunch of region servers. So the region servers are going to own some state in the world because remember, we can't have a database that multiple people are writing to because then you have all these state synchronization problems. So we're going to have one region server, which is like your game server, own one shard of the database. And then when a player moves from region to region, we're going to send their ephemeral state and also all of their persistent state to another region. We're going to tell some global server that we've set up, which by the way has its own persistent state, that we've moved regions, and then we're going to update the proxy server to make sure that it can relay the appropriate client to the appropriate region server so that it can talk there. We're also going to need to get some state from the global state, the global server and the region server onto the client. So it's a little bit complicated, and we're going to need to definitely use Kubernetes for this. So that's what we're going to need to do. We did get through it, though. So where does that leave us, right? So we did all of this work. We haven't started building our game, but where are we now? Well, we have a Kubernetes monstrosity. Dealing with the database is a nightmare. You need to shuffle everything through an ORM of some kind. You're going to need to be very careful if you're using transactions. And if you have transaction handles, you need to thread them through your entire application so that everybody has access to the transaction. Anybody who's dealt with web servers has run into this problem. You don't really get consistency checks because let's say you have a uniqueness check on a column. Well, if you're batching up your data before sending it to the database, you need to do those checks yourself because you're going to get an error later on, 5 minutes later when you go to persist. You've got to be careful where you're awaiting transactions because you need to be in an async context and also you can't block the frame processing for 30 milliseconds as you go to the database. Maybe that's a little bit high, but something like that. Multi-threading is complex because you need to make sure that, yes, only one thread is writing to the database data because we don't want to get out of sync again. Yeah, so it's a little bit tricky. By the way, also the ephemeral state is not really transactional. So you have this like transactional state in your database, but you have this ephemeral state in the world as well. So let's say you have health and you want to have somebody use a health potion. Well, the health potion state lives in the inventory, but the ephemeral state is the health. So I can't really do that transactionally. I can't update my health and make sure they don't cause an error to be thrown, and then my health potion doesn't get deleted. And I have like infinite health potions or something like that. So that's a challenge. Also, we only support one type of client. The server knows exactly the state of the world that the client needs to know, the area of interest and all of that stuff, including the global state. And if I connect a client, it's assumed that it's a game server client, and it's going to be a normal client. So we can't really have any like admin clients. We can't really have any AI clients or something that's going to be regrowing the trees or anything like that without building a whole new API on top of it. Not so easy to debug the server state. So all the ephemeral state that's locked away in objects or something, or if we're lucky, it's ECS and they're in sort of pages or tables, we have to write some code to debug that state. And we have no fault tolerance, and we're not even really dreaming of fault tolerance at this point. You have almost no hope because you have to do all the ephemeral state in there. So that's where we are, and we did a lot of work to get there. I ask the question now, is there maybe another way? Could we think about something a little bit different that would solve some of these problems? I argue that there are essentially 3 major complexities with the traditional architecture that we just set up, and they're all significant problems for us building our game. Number 1, we have the whole server database synchronization problem. It's complex, it's slow, it's failure prone, we can have gold dupe bugs and all kinds of crazy things. And that's something we have to spend a lot of our time dealing with. And everybody has to worry about this because it's entwined with the game logic. So if you have a gameplay programmer, they need to think about this. The other problem is we had to do a lot of work to set up a client-server state synchronization from the get-go, and it's very inflexible. So we set all that up, we did all the transport, we did all that stuff, but at the end of the day, we only have one client that we connect. And then because of the other 2, really, and all the complexities therein, we also have then deployment complexity. We have all these processes, and they're all talking to each other, and it's all very, very complicated to deploy. So now you need a deploy team, and you need you know, sort of a DevOps team to help your developers get started. And we're at, I don't know, 80 people at this point. How can we address this is a good question. Is there another way? Can we do something else more simply? Well, let's talk about each of those problems. So I think we can address the first problem by just merging the server and the database. And you can think of this either as we're going to take a real-time, we're going to take a game server and we're going to turn it into a real-time database. We're going to take a database and we're going to turn it into a real-time database, and it's going to run procedural code, just like our game server did. Or you can think of it as taking a game server that runs procedural code and giving it ACID properties. And for those of you who are not familiar, that is atomicity, meaning all transactions happen all or nothing. They don't half happen. Consistency, which means like our uniqueness constraints are guaranteed. Isolation, which means we can multi-thread it and nobody can tell. And durability, which means we're not going to lose the data if the machine restarts. Plus a query engine. So it's the same thing, but you can think of it either way as those 2 things. So yes, so that's one thing we can do. The other thing we can do is we can use queries to synchronize the client. So instead of building rigidly into our server application a algorithm for sending data to the clients and which data is going to be sent, instead we can connect clients directly to the database and have them query it in a way that the database is going to send down updates in real time. So in that case, that's going to handle the transport layer for us. It's going to handle the serialization format for us. It's going to handle all the type safety and code generation for us. It's going to handle the interest management because each client is dealing with its own interest management. It can say, for example, subscribe to all the players that are near me, plus this global data, plus my friends' chat messages and stuff like that. So basically, instead of this, which is the normal architecture, we're going to do this. And because we're putting the database in between your game server and your client, it can do all of that for you, right? So we don't have to actually re-implement all that, the transport, the serialization, everything, for every game, by the way. And the last thing is a database is a single binary. So we can just deploy a single binary, and we can upload our logic into the database. We are done with deploy. There's not really a lot of complex there. The database will handle replication, so it will replicate the data onto multiple machines. Fault tolerance, if our database or game server crashes, it will fail over to another machine automatically. This is something that people have been doing in databases for a very, very long time. And it also will handle all the proxying, so we don't have to build a proxy server and all this, the networking and all that stuff. The database is just going to route it to the appropriate place on the server, no problem, or on the collection of servers. So that becomes as simple as, you know, spacetime publish Bitcraft, and that is how we deploy our game. So just to give you a sense of how we would scale in this architecture, instead of it being a complex set of services that we set up, we have a set of nodes, 4 in this case, and then we're going to have each of the databases live on the nodes, and the database will route between them for us. So the proxying is handled by the database. It's all fault tolerant. There's fewer services. We just have one binary. It's symmetric on all the machines. And just like communication with clients, the communication between database is built in. We handle that for you. Let me see here. I will also note, I suppose, that Bitcraft is one of the hardest games to scale. If you have a match-based game, it's trivial in both architectures. So for the traditional architecture, you just throw up some game servers. You still have to deal with the state synchronization with the database, but obviously in this case, you can just throw up some more databases and call it a day. We're going to now go into a demo, so we're going to pray to the demo gods a little bit. But that's all great in theory, but let's see how it works in practice. How would you actually build something inside of a database? What does that actually look like? So let me flip over here for a moment. OK. So we've got the way this works in SpacetimeDB is we write our code in principle, any language that compiles to WebAssembly. In this case, we have a Rust project set up. And you compile that to WebAssembly, and then you upload that to run as sort of a stored procedure inside of the database. Let's see how that goes. We have here inside of the module, I guess you guys can see that. Maybe I can make it a little bit bigger. A couple of types. We have a standard vector type. We have we have a couple tables, but this is the one that matters the most. So we're defining a table here. The name is circle. It's a public table, meaning that anybody can read from it. We have a circle ID that's set up as the primary key. It's auto-incrementing, so we don't have to deal with any of that stuff. We just have a position vector and a velocity vector and a radius inside of this table. Each one of these fields is going to become a column in the table. We also have a timer table, which we'll go into a little bit later. And we just have sort of a global config table to store how big is our arena in here as well. The really cool thing here is that let's go deploy this, I suppose. So let me pull up this here. I already have that there. But I'm going to go deploy it, and I'm going to delete the old one that was there. And so we just deployed the whole game server to the backend. And now what I can do as well, by the way, is there won't be any rows in here yet, but I can, if we go a little bit back, we can actually SQL query the circle table. So here I have a query here, select star from circle, and we can see there are no rows in that table. But then what we can do is we can go back in my history here. We can call the add circles function. So let me just show you that function really quickly. It's a super simple function. It's called a reducer. You can think of it just as a mutation on the database. It's a regular RPC call. And I can call it from the command line. So here we're just inserting a circle into the circle table. So let's go do that. So if we go over here, let me connect to the database first. So this is now our application that's running. I can call the add circles function, and we have a circle. That's exciting. It's bouncing around. Isn't that fun? We can add a lot of circles. So let's add 100. This is pretty cool. Look at all the circles running. That's kind of fun. But now we're going to do something that kind of blows your mind. So you might notice we have all these circles. They're moving around. That's kind of fun. There is a problem, though. They're not really colliding with each other. We haven't done any of that stuff. Now, I just want to stress all of this physics sim is being done inside the database. This is running as a stored procedure. Every frame you're seeing here is transactional. So the positions all update transactionally and atomically in real time. So what are we going to do? We shipped our game. Players are playing it. A lot of players are playing it. In this case, only one. But in principle, maybe thousands. We don't want to take the game server down. Maybe what we could do is just change the server code without actually disconnecting any clients in real time in a way that they can't even really detect, except that the game's behavior changes. So what we're going to do, and this is a fun one, is I'm going to go here, and John has, my colleague here, John, has written a fix to our bug, which is that we don't have collision. So I'm going to go get that code here. Here's his branch. He has a new simulate physics function, and we're going to take that function here, and oh, isn't it very nice? And we're going to just go over here, and this is my module that I wrote, and this is my old function. You can see it's much shorter. And I'm just going to replace it. Okay, we're going to save that. It's looking good, no compiler errors. We can see what we changed here. And I'm just going to go back over here. And without disconnecting the client, you're going to have to watch carefully because it's going to happen fast. In fact, maybe I'll add a couple more circles so you can see. Right, here we go. It's a lot of circles. We're going to run the publish function to republish the database. And you're going to see in real time all of those circles begin to collide with each other if this goes as planned. They did. Well, that's exciting. I might have added a few too many circles. But there you go. So in real time, we updated that. And it is now, they're all colliding, and that's happening in real time, obviously, as you can see. So that's pretty fun. I challenge you all to think about how you would do that in a regular game server, because you have to replicate the state in the new server logic without going down. So that's something, that's a little homework for you to think about. We can also do now, like, let's say we do a SQL call on the database. We can see the positions of all those circles in SQL, super easy for debugging. I could also set them. You will not be able to tell because I've added way too many circles, but there you go. We can also look at the logs. So let's look at the logs for this. So spacetime logs, GDC demo. Whoops, I've spelt it wrong. So in the logs here, you can see this is the physics tick. It's taking hundreds of microseconds to run. I think we can get that even faster, but obviously you can do a lot. This is a super naive algorithm where we're just doing n-by-n collision detection, which is obviously not how you would want to do that in the real world. But John vibe coded this in like an hour or so it's something that you can do very, very, very quickly. So that's the demo. I think it's a pretty incredible workflow to be able to just update your game live running. We've had my co-founder fixing bugs 30 seconds after a user reported them by just updating the module code without taking anything down. So let's go back to this. I want to make sure I have some time. I do. Where is my presentation? There it is. OK. So that was the demo. So let's talk a little bit about how this works under the hood, because I've had a lot of people come up to me and say, how is this possible that you're doing this in a database? I think that nobody ever tried it, I suppose, or if they did, there were some details that mattered and caused problems there. But it turns out it's totally possible. You can just do it. So this is an example of how the database looks internally a little bit. So when a client connects, they connect to an HTTP server. That HTTP server routes to the appropriate WASM instance. And to just talk a little bit about that, WebAssembly, for context, is I actually have it written down. It's a memory-safe binary instruction set, which is supported by browsers. They built it because they are running arbitrary code execution, and they don't want that code to be able to escape the memory of the instance. And so that's very important for us since we're running a multi-tenant database. And we also wrote the database in Rust for that reason, so that we have memory safety and there's not memory safety issues there. That WASM instance is what's running all of the physics logic that you just saw in the code. Those functions talk to an in-memory data store, which has all of the, in the case of the tables, all of the circles laid out in memory. They're cache aligned. They are packed very tightly. When we copy them over into the WASM instance, we do so very efficiently. We basically just a mem copy over, so it's incredibly low latency. For context, single index lookup is about 300 nanoseconds, so that this, let me see if I can, this link is very small. It's in the nanoseconds range, 300. I think we can get it down significantly from there, because that's also counting all the index lookup stuff. There's also a query engine. The query engine is the thing that will run the SQL, and it can both read and write to the in-memory data store. The only person who can write into the in-memory data store, though, is the owner of the database. So the way that clients interact with the query engine is that they run what's called subscription queries, and those subscription queries are evaluated in real time every time a transaction is run to send only the delta of what has changed in the database to your client, because that's very important when you're updating a lot of rows. And then in the background, we also have this thing called the commit log. The commit log is essentially a write-ahead log for those of you who are familiar with databases. It stores the full history of everything that ever happened in the database. And we compress and archive that log when it gets particularly long. You can also truncate it if you want to. And then we also have a snapshot tree. And the way that works is any dirty pages that have changed since the last snapshot, we write to a file so that we can start up very quickly. So we can start from the last snapshot, bring up the database state, and then replay the log very, very quickly to get back to where we started. Notably, we have chosen at this point to implement synchronous commit off, which is a feature, for example, that's in Postgres, which means that we will actually deliver to the client the results of the reducer before they've been persisted to disk. We haven't yet implemented synchronous commit on, which is what you would probably want if you had like an e-commerce website, but that is something that we're planning on doing. And that would just add to the latency, but not the throughput of this. And for context, I suppose, people have asked me, how can this possibly be writing to disk that fast? Well, my laptop has about 5 gigabytes per second throughput to the disk. And for sort of reference, that would be like updating 2.7 million players' transforms 60 times per second to saturate that. So the disk is really not the limiting factor here at all for the throughput of this. The other cool thing that we can do here in terms of how SpacetimeDB works is, let's say you wrote your module in C#. The way that then gets compiled down to the WebAssembly module allows us to spin up that WebAssembly module, extract out the schema information, and then we can code generate different clients for your module. So for example, we have over here, if I go up one directory, we still have our thing going to town there, a TypeScript client for this. And if I go into the index file, you can see we have like the add circle function that we can call directly from the client. So we've co-generated all the types on all platforms that you need, and you can have a web client, and you can have a game client. And we really hope that this is going to help people build multi-platform games in the future. Let me go back to this. So just want to do a brief recap here. Where does this change leave us in terms of our improved workflow? Well, ECS is implemented by default. So the way that the page layout works internally is very similar to ECS. You can think of ECS actually as sort of a subset of the relational model, where you have a table which is the entity ID table, and then you have all your other tables have foreign keys to the entity ID table, and it's approximately the same. There's a lot of performance details there, but that is more or less the model. So just get that out of the box. And by the way, you're not forced to make things that aren't entities. So we didn't even make circles entities, or you could have chat messages, which are maybe not entities in your game, whatever you want to do. You have type-safe RPCs. So now on the client, you didn't have to do any work. Just automatically out of the box, you get to call your functions on the server just for free. All the networking serialization and deserialization is done for you. So we currently use TCP as our transport layer. In the future, we certainly can add reliable UDP and a bunch of different interesting techniques for that. You don't have an ORM anymore. You're just in the database. Everything is persistent. All the player positions, all of the movement, the transforms, everything just automatically goes in the database. Your game developers just never have to think about that literally ever again. They just forget it. So the database nightmare has ended. It's over. We're done. You can have many clients. So we have, in Bitcraft, we have like a bunch of agents that respawn trees in the world or update the health of players, or we actually split the AI processing across multiple machines, and we have them just act as agents in the world. So that's one thing that we can do. Debugging is super simple. You can just SQL query your game state. You can say, oh, I want to check out how this animation looks if my health bar changes, and you can just go into the game state and say SQL, like update table set health to be 500 where the user ID is mine. all the real-time broadcasting we do for free, and we also, by the way, multi-thread it like crazy. So this is something that, because we handle all of it, we can just keep hammering away on this and making it even better. In fact, eventually we can actually split it up into multiple machines and without you needing to care about that, and then implement the subscription evaluation across multiple machines, which is important because in an MMO, to get people into the same place, you have an n² problem where for every update that one client is doing, n other clients need to hear about it, and if they're all doing n things, it's n times n. You get replication and fault tolerance for free. So if a game server goes down, well, it's just a database, and we can fail over to another replica that is already running. So it's just easy. Deploy is a single command. So we've addressed a lot of the problems that we ran into in the previous iteration of this, and it's just a property of databases in general. The only thing you really need to do is make it fast enough and have it be procedural so that you can write all the complex logic that you've been writing and that you're familiar with in your game server previously. I should also mention all of the reducers that are running, they're atomic by default. So if you're going and you decide like, oh, there's something wonky about this transaction or this player's not high enough level, you can just return an error and all of the changes you have staged will get rolled back. So that's important. I don't have that much time, so I briefly just want to talk on a little bit about future work, things that we can do that are very exciting in the future. So this is stuff that we have not built yet, but that could be really exciting for things that just come naturally from databases. One is more aggressive multi-version concurrency control. So multi-version concurrency control is a form of optimistic concurrency control, which says, hey, we're going to parallelize a bunch of transactions, assuming that they will not conflict. If they do conflict, we're going to detect that anomaly, and we're going to roll it one back and try to replay them serially, essentially. This allows us to just multi-thread your applications without anybody having to think about it. It just happens. And this is something that databases have been cooking on for a very long time, 50 years. So it's something that's very important. The other thing I'll say with this is there's a lot of different concurrency primitives that databases have talked about, so MVCC is not the only one. And databases also have a very principled way of you relaxing what's called the isolation properties. So you could say, hey, I don't really care if two players attack at the same time if they both kill each other. I don't need those to be ordered sequentially, so I'll just let them happen. And so you can relax these constraints and just allow us to do greater scale by allowing certain isolation anomalies. You also, by the way, just get rewind and replay support for free. So we store the full history of all your transactions in the log. And so we can just set the game state back to where it is. Actually, if people have questions, I have a little demo on that from like 5 or 6 years ago that we did, showing you following a player around in-game at like 8 times speed as they go and pick up all the stuff. And you don't have to write any code for that. It just comes for free because we have that capability in databases. And there's a lot of optimization details here that you want to be aware of, like how we're going to compress things. Could we do deterministic simulation and then not store the outputs but store the inputs? There's a lot of things you want to talk on there. But that's something that's super cool. And then another cool thing I want to talk about, which is not something we do today, but we could certainly do, is automatic client-side prediction. So inside of Bitcraft, we implement client-side prediction for all the movement stuff on top of SpacetimeDB. And that means that we change our local state, and then we send the request to the server, and when it comes back, we see if it did what we actually expected it to do. Otherwise, we roll it back. In the future, we can actually run SpacetimeDB locally inside of your client, and then you have all of your server logic locally inside of your client, and you can treat that local database as the actual database. And as you make changes to that, we will send changes to the backend and reconcile them automatically for you with all the rollback and roll forward that you need to do that. So that's a super exciting thing that I would love to do. We're not there yet, but that's a pretty fun one. Okay. I just want to leave some parting thoughts. I only have a couple minutes left before we're going to get into questions, which is essentially the dream here is that we want it to be possible, and I think it totally is, for 1 or perhaps 2 developers to be able to make an indie MMORPG. A lot of the complexity that we've been dealing with for these types of systems do not need to be that way. I think there's some things we can do to improve that, and I think this is completely possible, and I would love this dream to live. The other thing related to this is I think a lot of people have a very constrained idea of what a database is. They imagine it to be, okay, it's Postgres, it's slow, it does SQL, it writes to disk only. But if I could have you take away anything from this talk, it's that databases are really more of a way of thinking, more than they are a particular piece of software. It's about thinking about your data like structured data and how we can use techniques to manipulate that data. It is, unsurprisingly, much related to data-oriented design. There's about 50+ years of research, probably more, into databases that people have done, and I think we ignore it at our own peril. You know, there's querying data, there's separating the physical representation from the logical representation, so that would be allowing you to access your data regardless of whether it's struct of array or array of struct and all that kind of thing. Multi-threaded processing, indexing, you name it, they've been thinking about it, and ultimately we're doing the same thing with our program memory as well. ACID properties do not equal database. You can totally have a database that has some or none of these process properties, and so I think we should kind of open our minds and think about that a little bit more generally. Program memory is a database. This is one that is very interesting. Originally, Edgar F. Codd invented the relational model of databases, which is, by the way, not the only model of databases. In like I believe it was 1970, because hard drives had a bunch of pointers in it, and it was very hard to traverse that data. You had to build a program that would actually walk through all that data, and he wanted to build a way for you to query that data without having to deal with the physical properties of the machine. And so largely what Edgar F. Codd was proposing was to remove pointers from our data model. Pointers are an implementation detail. They say something about the physical representation of the data, but not the data itself. And I think we would benefit a lot from viewing our program memory in the same way. There's sort of a logical set of data that we have, and then there's a physical representation of that data. And if we can draw a clean line between them, there's some very, very cool things that we can do. We can change a lot of our program without changing the physical representation, and we can change the physical representation without needing to change our program. Okay. The last thing, of course, is data-oriented design, I think, is very much so in the direction of database-oriented design. Obviously, the principle of data-oriented design is that all programs exist to transform data from one form to another. We ought to think about how to do that most efficiently and most flexibly. And I think that database-oriented design is maybe the next step in that journey. So if I had to send a message to you, it would be, let's make our designs a little bit more database-oriented. And with that, I would love to take questions. So if you could come up to the microphone, I'd be happy to answer any of them. Sorry.
Hello. Testing. Okay.
Yep, I can hear you.
All right. So first off, great talk. Very interesting. I hope I'm not jumping the gun a little, but you talked a little bit about implementing data analytics in some of your early slides.
Yes.
So I was wondering what your early thoughts are on setting up architecture for both reporting and predictive analytics for future player or business use case in your MMO.
Yeah, that's a great question. So the original concept for SpacetimeDB, I used to work at a company called Machine Zone. They did large-scale mobile games, and I was in the data science and data platform department. And they always wanted to have historical data, but they had to kind of try to reconstruct it from the existing data. Actually, one technique they used was to snapshot the database every 12 hours. And the problem with that is, A, you don't have the interim period, and B, you're copying a lot of data that hasn't changed. So that was, in some sense, the inspiration for storing the full history. And so things that we could do in the future is give you, and we plan to do this, give you access to that commit log so that you could run over it, and you can build graphs of, like, for example, what's the CCU graph after the fact. So you can calculate the concurrently connected users. You could show users things like what was their the gold that they had in their inventory over time, because all of that data is there. We would love to be able to do some automatic analytics for you, so we could do things that are generic to every game. For example, like day 1 retention, day 10 retention. We could do things if you give us certain events that you want to track, like, hey, did a player get to this level? Then we could automatically provide that to you. Ultimately, we'd love to give people a set of dashboards, or at least a dashboard builder if they want it, which would let them build their own queries on that data in the future.
Thank you.
Cool.
So my question is related to scale. So
Sure.
the vast majority of games are playable on a device. You load a game on a device, the binary is loaded on the device, it uses its memory, et cetera, et cetera.
Yep.
The system that you're describing here basically says the game exists remotely. Everything is happening remotely. And so I just have, so with a web browser, I have a window into this reality. So given that the game exists remotely, given that the vast majority of the resources are now going to be server-side, how does this, what is the cost of the scale here, and what are some of the design considerations that you have to be aware of when you're thinking about building an MMO, or maybe something even more complex?
Okay, so the first thing I'll say is this doesn't necessarily require that it is remote. You could, as I mentioned, in principle, run this locally. We haven't focused on that because we have an MMO, and the state of the world is too much to synchronize to clients. So in our case, we needed to do this first, if that makes any sense, rather than run the database locally. The next part of your question was, okay, what considerations do we have to think about when we have this scale? So you have to really think about, I suppose, mainly 2. How much on the server are you going to do in terms of physics calculations and all of the complex things you're going to do there? Necessarily, the less compute you do, the more players you're going to be able to get into a single database. But yeah, it really depends. I think the thing to consider is that computers are very, very fast. If you set up cache efficiency very nicely, you can do a lot of things. We had a micro benchmark that we did that demonstrated we could do about 1 million updates to positions of a vector in about 200 milliseconds. For context, I think that's probably still 200 times more slow than it could be if we continue to optimize. So you want to set up your data in a way that's cache efficient for computers. We still need to have the data-oriented design approach of looking at how are these things going to be executed. The other thing you want to think about when you have something like an MMO is managing your network updates. So you want to make sure that the data you're sending down to clients, the data that the clients are subscribing to is as minimal as it can be. And that is more flexible to do when you have all of this query stuff. Whereas if you have like, oh, I have a front-end game engineer or a game engineer that's working on the client, but the server engineer decided to send me all this stuff and I don't really need it, there's not really a way to update that unless you want to get your hands into the server as well. So.
Gotcha. Thank you.
Cool.
I'm just curious about how, like, say you're writing an MMO that has like physics simulation going on, so you have your typical simulation loop that's like querying all the objects that might be changing,
Yep.
and then like modifying their state. Are you essentially in that case of SpacetimeDB doing like at the beginning of the frame you're doing a read on all the state that you're potentially mutating, and then at the end of the frame you're doing a publish and essentially a write, or is it something else?
Yeah, that's correct. I can actually just show you the code. So this is the one where they are colliding. So we're doing all the collision logic here. Check if the circles are overlapping. It's all well commented because ChatGPT wrote it. And at the end, we do an update on all the circle entities. Well, yeah, circle rows.
Okay, got it. And then just a quick follow-up on that with if you're thinking long-term doing client-side prediction.
Yes.
I forget if there's a like local view of was there a local view where you would potentially be able to use some of this code for the prediction, or is
Yes, so let me talk a little bit about how it works now and how it could work in the future. So right now, we actually store what we call the client cache in every of our SDKs. So if you have a TypeScript SDK, we're going to do the SQL query. We're going to keep a store of the data. It's like a replica of the database state locally that is immutable. And so instead of mutating that state, you're going to talk to the server, and then that's going to filter down the state, and your state updates. And you react to that state. And it's very reactive. That's why they're called reducers. I actually stole that from Redux, which is a web framework. So that's how it works today, and we give you ways to like query that and index on that and stuff. In the future, we actually want to have the client be a partial replica of the server state. So we actually want to take the SpacetimeDB code and run it locally in your client, and then have that reconcile between it so you don't have to think about it. And you just think about your local replica, essentially.
Okay, cool, thank you.
Cool.
Hello. So first and foremost, I want to empathize with you guys. These are not easy problems to solve. I've been a developer in this space for my entire career, pretty much. And my question really, because you guys didn't really touch on it that much, or maybe did a little bit, was around support and operations. So obviously you talk about we're going to be able to deploy real time without having to bring the server down, but what's your plan long term regarding, suppose this thing blows up and now that you have 100,000 concurrent players and, oh, replication gets disconnected. Oh, you have a split brain. Oh, you have to reseed or restore to another target. Like you have all these considerations that's like, oh, we're going to have an operations person just go in there and write a SQL query and everything's fixed. And it's like, I don't know about that one, guys. So what's your plan if this thing really, becomes a big thing? Do you really think you're going to be able to support scaling that with a team of 40 people, like you said?
So this is a good question. I think so. I guess let me ask a clarifying question. Are you asking more about how we're going to run SpacetimeDB as a product operationally, or are you saying how would I run SpacetimeDB for my own game on my own servers?
I guess as a product, like envisioning this as like a multi-cloud, because I loved how you have a multi-tenant database, and you talked about we have this Kubernetes monstrosity, and it sounds like there's a lot of contentious stuff going on there. But how would you? If this thing was in production and something goes wrong and you have lots and lots of players, how do you address some kind of a failure?
Well, I don't mean to at all trivialize any of the problems. I think database administration is a very complex problem, and you need to take it very seriously. So the first thing, of course, is we need to make sure our code is tested, right? And that means both for correctness and for scale. So doing scale tests, making sure we can do that. Ultimately, every complex server backend company needs to deal with this. I don't necessarily think that we will be hitting that kind of scale with only, so the company is 40 people, but the SpacetimeDB team is actually only 14 people. So it's a much smaller thing, and I'm looking absolutely to grow that team to manage it. What I will say is, it was going to be hard anyway. It's going to be hard to build this kind of backend, no matter how you are going to do it. I think it makes it easier to formalize it as a database, because you can start to think about the problems become, instead of unique to our situation, they become general problems that people have been thinking about for a long time in databases. I don't think there's an easy answer to this particular question.
Good luck to you guys.
Thank you.
Hey man, first of all, great talk. Loved everything about it. My main question is more so around security.
Sure.
So, what are some of the ways that you guys are addressing, bad actors, security concerns, things like that, especially running an MMO where people are always like to try to find ways to exploit, et cetera?
Okay, I will answer this in 3 parts. The first one is, for things like mutations, we always force clients to go through your server code, your reducers, these things that we have up here. So this is really not a different security model from what you were previously doing on your game server, with the exception of it's a little bit better because it's atomic. So you can't run into a situation where a player knows how to throw an exception inside your code, and they're going to have you half do something, and then your state is all messed up. So we have that protection for clients for mutations. So that's one part of it. The next part of it is for reading. And for reading, because we have to do incremental query evaluation for performance reasons, we have you implement your row-level security rules in SQL. And the reason for that is we need to be able to, with just the input delta, compute the output delta. And so we actually have that in a language which we can sort of take the derivative of and get that. In the future, so that's how that works, and those are all evaluated per client in real time. That's actually not out. We have somebody who's making a commit today to get that in. That was supposed to be 1.0, but we didn't get there in time. We really tried. So right now we just have public and private tables, but as of like maybe next week, we're going to have row-level security. One thing I'd like to evaluate for row-level security in reading is could we do procedural versions of that. The only challenge there is you can't take the derivative of them, so you have to recompute the entire thing, get the whole output set, and diff it with the existing output set to find out what I need to send to the client. So that's number 2. And then the third one is, obviously, there's DDoS problems and protections. So we have some very basic ones. We have, for example, like row limit, which limits the amount of rows that a particular client can query. But ultimately, we want to do what we call energy, sort of cost-based rate limiting for users. So you can say like, hey, look, I don't want to let anybody over the course of a minute use more than this much energy is what we have it called, but it's basically just the cost of it. So those 3 things are the things that we're thinking about most for security.
Awesome. Thank you, man.
Yes, I will. I think let's do maybe one more question, and I can also go back to the end. Can we do? Yeah, one more. Yeah.
Hi. How do you deal with multi-region latency?
Say that one more time.
How do you deal with multi-region latency? I assume you have a multi-region setup?
I'm not sure I can hear you. What about latency? I know it's latency.
Multi-region.
Multi-region latency. We don't deal with it right now.
Okay.
So we just don't. It's all in Virginia. Eventually, we can do that. Obviously, we're building an MMO and a database, so we will get there, but not yet today. Last thing I want to just shout out before we leave is I'm going to be in the whatever the rooms are that we go to that you want to ask me questions in. And then also, if you want to come here, we have $200 cloud credits if you want to sign up to the SpacetimeDB website. So up to you. If you want to mess around with it, give it a try. Thank you all very much. I really appreciate it.